Welcome to Cup of Tea Mathematics classes. Gurubhyo Namaha. This is your Murali Krishna. This is the first video on the calculus or single variable calculus. In this video, I am going to discuss about some real analysis concepts. Now, everyone, you know what is a real number set. These real number set have so many subsets. For example, the natural number set is a subset, or rational number set is also a subset, and say irrational numbers or whole numbers or integers, all are subsets of real number set. Other than these, we have some more subsets. For example, I write a set like this. A is equal to, say, 1, 2, 3, 4. First 4 natural numbers. Now, in this set, the first element is 1, and second element is 2, third element is 3, and fourth element is 4. Okay, similarly, I have, and these type of sets are called discrete sets. These type of sets are called discrete sets. Why? Because you can discretize the elements. Whereas suppose say I need all the real numbers, say one such that 1 less than or equal to x less than or equal to 2. That means all the real numbers I want between 1 and 2. Okay, I can write this also in the form of the closed interval 1 comma 2. Now in this is a subset of real number set. Here the first element is 1. The first element of this set is 1. And what is the second element in this set? You cannot identify. Why? Because there is no next real number to 1. If you say 1.1, no, 1 point, you can get a real number less than 1.1. If you take 1.01, then also you can get. So you cannot identify what is the second element, third element, and so on. These type of sets are called continuous sets. These continuous sets are also called intervals. Now let us start my lesson with the concept of intervals. What are the intervals? Intervals are continuous subsets of a real number set. So intervals. Intervals, this is a concept. Intervals, these are the continuous subsets of real number set R. Okay, then let me write different types of continuous sets or intervals. Number one, I want all the real numbers. Let's say, for example, here, let A and B belongs to R and A less than B. Okay. Let X belongs to R such that the symbol is such that A less than or equal to X less than or equal to B. I want all the real numbers between A and B, including A and B, and this is denoted by A comma B. Of course, this is called closed interval. But in advanced calculus, we have very nice definition for closed set. It is just closed interval now. The next one, the second one is let x belongs to R such that my A less than x less than B, and this can be written as A to B. It is called open interval. In this one, all the real numbers are included, but the A and B are not. So, set of all the real numbers between A and B, excluding A and B, is an open interval. Next one, we have so many like this. A less than or equal to x less than B. This is A, B, left closed, right open. In some textbooks, it is also written as A, B, open. So this symbol represents open. Next one. Let x belongs to R such that A less than x less than or equal to B. So this is A side open, B side closed. And of course, these intervals are finite intervals because bounds are defined, upper bound and lower bound. Now I have another. Now let x belongs to R and x is more than or equal to A. That means I want all the real numbers more than A, and that is denoted by A to infinity, A side closed, B side infinity. Next one, similarly, we have let x belongs to R such that x is more than A. That means I want all the real numbers more than A. So here this can be written as A to infinity. The next one, let x belongs to R such that x is less than or equal to A. That means I want all the real numbers less than or equal to A. Then let x belongs to R such that x is less than A minus infinity to A. Here A is not included. This is about continuous sets or intervals. Some are finite intervals, some are infinite intervals. Next one, I am going to discuss about a very important concept, that is absolute value of real number. Absolute value of a real number. This is my next concept. Absolute value of a real number. Let's say x is any real number. Its absolute value is denoted by the symbol, this one. And how do we read? Read as modulus of x. How it is defined? It is defined as mod x is equal most of the textbooks we find this definition is very simple. X, mod x is equal to x when x is positive real number, positive real number, and whereas minus x when x is less than 0. For example, I want to go for x is equal to plus 2. When x is equal to plus 2, I have mod 2 is equal to, since 2 is more than or equal to 0, so you have to take mod 2 is equal to 2. Same thing, if I go for x is equal to minus 2. Now here, mod of minus 2 is equal to, mod of minus 2, since minus 2 is less than 0, you have to go for like this, minus 2, so this is equal to plus 2. So the definition. And we can define this in another way also. Under V is mod x is equal to maximum of minus x, comma x. Same thing here. For example, if I have x is equal to 2, then mod 2 is equal to maximum of minus 2 and plus 2. Of course, maximum of these two sets is equal to 2. So mod 2 is equal to this. X is equal to minus 2, then mod of minus 2 is equal to maximum of minus x, that is minus 2 and minus 2. Of course, minus of minus 2 is plus 2, so this is the absolute value. This is what actually absolute value means in the real analysis. Absolute value of x means the distance of x from 0. The distance of x from 0 on the real line. I will explain. So here, mod x is the distance of x, of course a real number, from 0. That means you take a real line, put here 0, you are moving x units distance on the real line from 0. It can be either positive side or negative side. If it moves right side, then the position will be plus x. If it moves left side, the position will be minus x. Of course, the distance between these two is same as distance between these two, because the distance is always positive. Now, let me discuss some properties about this. Mod x properties of mod x, where x belongs to R. First, number 1, mod x is always more than or equal to x for all x belongs to real number set. It's obvious it is. Second one, if mod x is equal to some example a is a real number, this implies x is nothing but plus or minus a. The second thing is, if mod x is less than or equal to a, this implies my x value lies between minus a and plus a. And next one, of course, I can write mod x is less than a means minus a less than x less than a. Here in this case, all the real numbers between minus a and plus a. So I can write it as a closed interval. Here I can write it as open interval. Let me write it also. And this implies my x belongs to minus a to plus a closed interval. So here mod x is less than a implies minus a less than x less than a, or this is same as x belongs to open interval minus a to plus a. Next, let me write one more. Mod x is more than or equal to a. This means my x, somewhere here, this is a, for example. My mod x must be more than a. What is the meaning of that? My x will be either more than a or less than minus a. So in this case, what happened? This implies here my x is less than or equal to minus a and x is more than or equal to a. Sorry, or. So this is nothing but minus infinity to a minus a union a to infinity. I am going to use all these notations in my numerical questions, so you have to learn very carefully. Next one. Mod x is greater than a. This implies x is less than minus a and x is more than a. This implies I can write minus infinity to a, both sides open, union a to infinity. And very important properties. Number one, mod of x plus y is less than or equal to mod x plus mod y. And mod of x minus y also less than or equal to mod x plus mod y. Mod of x minus y is more than or equal to mod x minus mod y, of course whole mod. And about product, mod of x times y is equal to mod x times mod y. And mod of x by y is mod x by mod y, of course y is not equal to 0. Now I am going to prove these two properties because they are very important. You cannot say obviously. Now strictly I am going to prove by keeping the point a real number concept point. Of course in complex numbers we have different proofs. In vectors we have different proof. Okay, but I confirm to only real number set. Now number one, first property, mod of x plus y, mod of x plus y whole square. X comma y belongs to a real number set, and this is nothing but x plus y whole square. Because mod of x plus y whole square positive, x plus y whole square also positive, I can write like that. So this is very simple, x square plus y square plus 2xy. Now this x square can be written as mod x square because positive, and this is mod y square. I cannot write like this. Let this number one. So I have mod of x plus y whole square is equal to mod x square plus mod y square plus 2x square. Now I am going to use this concept. Mod x is greater than or equal to x for every real number. So here I can write x y less than or equal to mod x times of mod x y, or we can write 2xy is less than or equal to 2 times of mod of xy. If you don't want to, no problem. Now I have a inequality a less than or equal to b. If I add a positive quantity on both sides, inequality sign will not change. That implies a plus c is less than or equal to b plus c, provided c is greater than or equal to 0. Now here what I do, I have 2xy less than or equal to 2 times of mod xy. What I can do, I can add both sides mod x square plus mod y square. Of course this is t is 9 times nothing but 2 times of mod x mod y. This is true. Why? Because this already 2xy is less than or equal to 2 times of mod x mod y. Just I'm adding two positive numbers, so value will change. Okay. Now this mod x square plus mod y square plus 2xy is nothing but mod of x plus y whole square. Of course, mod of x plus y whole square less than or equal to mod x square plus mod y square plus 2 times of mod x mod y. This is nothing but a square plus b square plus 2ab. So this is mod of x plus y whole square less than or equal to mod x plus mod y whole square. By taking positive square root on both sides, we get mod x plus y is less than or equal to mod x plus mod y. Just simple proof this is. We can have same type of proof in vectors in complex numbers also. Once you know this, remaining proving is very simple. For this one, consider x minus y whole square. For this one also, x minus y whole square. Please take it.